Lesson 7 is all about expanding binomials using the binomial theorem and Pascal's triangle. We call Pascal's triangle a rectangular array of numbers where the first and the last number in each row is a 1. And each of the other numbers in the row is the sum of the two numbers that are above it. So let's say, for example, on this third row, we got the 2 by adding 1 and 1. And then on the fourth row, we got the 3 by adding 1 and 2, or 2 and 1, and so on and so forth. So the first number is 1, the last number is 1, and the other numbers in the row come from the previous row by adding the two numbers directly above. 1 plus 3 is 4, 3 plus 3 is 6, and 3 plus 1 is 4. First, we're going to look at the binomial theorem as it's related to Pascal's triangle. So for every positive integer n, when we expand the binomial to the nth power, we're going to take the number from Pascal's triangle, and then the first term to the nth power, and then the second number in Pascal's triangle. We're going to reduce that power on the first term, and we're going to introduce the second term. So we'll see how this goes as we go along. So in the a plus b to the third power, we want to expand that. Now we know from Algebra 1, if I multiply binomials together, we can only multiply two at a time, two numbers at a time. So let's take the second pair of numbers and save the a plus b for our next process. So a plus b quantity squared is a squared plus 2ab plus b squared. And then if we multiply this a times all of the terms, we're going to have a cubed plus 2a squared b plus a b squared. And then we're going to go back and multiply the positive b times all of the terms and get a squared b and 2a b squared, and then b cubed. So collecting like terms, we're going to see that we're going to get one of the rows in Pascal's triangle, noticing this power of 3 here, and going back to Pascal's triangle, the power of 3 is going to come from this row. It's going to come from this row, because this row is a plus b to the 0 power, and this is a plus b to the first power. This is a plus b to the second power, and this is a plus b to the third power. So it's this definition that's telling us the p sub 0, p sub 1, p sub 2, and so on is coming from this power and the row that corresponds to it. So this is my nth to the third power, or my a plus b to the nth power in this case. So we're going to get 1, 3, 3, 1 are going to turn out to be the leading coefficients in our expanded binomial to the third power. So we would have a cubed with a coefficient of 1, and then 2a squared b and another a squared b gives us 3a squared b, and then ab squared and 2 more ab squareds gives us another 3ab squareds, and then finally we have 1 b cubed term. So you can see that using Pascal's triangle, if you create the triangle, it would be easy to expand some binomials this way. Okay, so what happens when we expand and it's this difference of binomials? So a minus b times a minus b times a minus b And again, just multiplying the last two together, saving the a minus b for the third step. So a squared minus 2ab plus b squared. And then distributing the a to all three terms gives us a cubed minus 2a squared b plus a b squared minus a squared b plus 2a b squared minus b cubed. And then collecting like terms, we're going to end up with 1a cubed, but adding up the a squared b and the a squared b, we're going to have negative 3 a squared b terms. And then adding up the ab squared and the 2ab squared, we're going to have positive 3ab squared. And then finally, we're going to have minus 1 or 1 negative b cubed term. And here you should see the pattern that the 1331 is still there, but when my operation is subtraction in the binomial expansion, we're going to see that we have alternating signs in the row of Pascal's triangle based on subtraction. Example 3 lets us explore that connection between the triangular pattern. So anytime we have a number to the 0 power, by definition is 1. And a plus b to the first just means we have 1a and 1b. So a plus b to the first is just 1a and 1b. But when we expand a plus b times a plus b, we just saw that that gave us 1a squared and then 2 ab's and then 1 b squared. So there's where that row, that triangular pattern comes from. So you can see we got 1 and then 1 and 1 and then 1, 2, 1. And this one is going to be 1, 3, 3, 1. And the next row will be 1, 4, 6, 4, 1. But something really interesting is going to start to appear. So we're going to see that we have the 1 and the 3 and the 3 and the 1. But what happens to the terms, if you looked back at the definition on the first page, there's 1a cubed and no b. And then there's 1a squared and 1b. And then there's 1a and b squared. And finally, there's no a and a b cubed. And because our operation is addition, we're going to have plus and plus and plus in between. So our operation stays positive all throughout. And then finally, to put it all together, the pattern is 1, 4, 6, 4, 1 for the fourth power. And what's happening? The power of a starts out to our nth power, and there's no b. And then the next number, our coefficient on Pascal's triangle, is 4. Our power is reduced to cube, and then there's a b to the first. And then our next coefficient is 6. The power on a is descending, and the power on b is ascending. And then next we have another 4. So 1, 4, 6, 4. And the power on a would be, whoop, we got a mistake here. A, 4, 3, this was 2. A, 4, 3, 2. This is power 1, and then the b is going up. So b to the 1, b to the 2, b to the 3. And then our last coefficient is 1. The a drops off because it's a to the 0 and then b to the 4th. So the powers on a go power 4, power 3, power 2, power 1, power 0. And the powers on b go b to the 0 power, b to the 1, b to the 2nd, b to the 3rd, b to the 4th. So let's use example 4 to make a note of that. We've just discovered that the a terms descend. The a terms will be descending. And since our n power is 8, we'll be going from a to the 8th down to a to the 0. And we also discovered that the b terms are going to be increasing or ascending. And they'll start out in our first term. It'll be b to the 0, and we'll finish with b to the 8. And then the next or last piece of information we need to realize is that we're multiplying each term by the coefficient in the 8th row. And you got to remember that the Pascal's triangle starts out with the 0 row and works its way up sequentially. Okay, so we're multiplying each term by the coefficients in the 8th row of Pascal's triangle. And those coefficients are going to be 1, 8, 28, 56, 70, 56, 28, 8, and 1. Now I want to do this in color so you can see the beauty of all of this. So we've got 1 is our coefficient, a to the 8, and b to the 0. And our operation is addition, so our next number is 8, and then our power on a is 7, the power on b is 1. Then our next number is 28, so we have 28, a to the 6th, b to the 2nd. Next we have 56, a to the 5th, b to the 3rd. Now we're up to 70, so we have 70, a to the 4th, and b to the 4th. Then we're at 56, so we have 56, a to the 3rd, b to the 5th. And then our last few terms, 28, a to the 2nd, b to the 6th, 8, a to the 1st. I said b to the 6th and I wrote b to the 8th. Let's go back and fix that. B to the 6th, so b to the 7th. And our last term is coefficient 1 with a to the 0 and b to the 8. And if you notice on this entire process that every single term, the powers add up to 8. So we want to simplify and get rid of those 0 powers and then add all the terms together, and we're going to end up with a to the 8th, 8a to the 7th b, 28a to the 6th b to the 2nd, 56 a to the 5th b to the 3rd, 70 a to the 4th b to the 4th, 56 a to the 3rd b to the 5th, 28 a squared b to the 6th, 8a b to the 7th, and 1 b to the 8th. So we have expanded a plus b to the 8th power, and very carefully ended up with descending powers on a, and then ascending powers on B. 1, 2, 3, 4, 5, 6, 7, 8. In example 5, let's think about what happens when our B term is a 1. We know if B is a 1, 1 to the 0 or 1 to the 6th will always be a 1. So our coefficients on row 6, if we go back and check the coefficients on row 6, they're going to be 1, 6, 15, 20, 15, 6, and 1. So we want 1x to the 6th plus 6x to the 5th, and another times 1. Then 15x to the 4th, and 1 to the 2nd, which is still 1. So 20x to the 3rd, and 15x to the 2nd, and 6x and 1. So that was relatively simple. Now here's one for you to try. You can turn off the video and come back to check your work. This one is subtraction, so be careful. Now if you did everything right, row 4 coefficients were 1, 4, 6, 4, 1. And we need to have alternating signs because it's subtraction. So alternating signs, since the binomial is the difference. And that would be 1x to the 4th minus 4x to the 3rd plus 6x to the 2nd minus 4x plus 1. Did you get that right? In example 7, here's another way to take care of these types of problems. We know that row 5 has the coefficients 1, 5, 10, 10, 5, 1. So we have 1x to the 5th, and then we have 2 to the 0. Then we have 5x to the 5th with 2 to the 1st power. Then 10x to the 3rd. Whoop, I keep forgetting. 5, 4, 3, and then 2 to the 2nd power. Another 10x to the 2nd with 2 cubed, then 5x to the 1st, and 2 to the 4th, and then 1 with 2 to the 5th. So putting that together, this is 1 times x to the 5th. And this is 2 times 5, so we have 10x to the 4th. And this is 4 times 10, so 40x cubed. And then 8 times 10 is 80x squared. And 16 times 5 is another 80x to the 1st. And then 2 to the 5th is 32. Are you ready to try one on your own? Turn off your video and give example 8 a try. So if you set up your problem right, you know that you need 1, 3, 3, 1. And this time it's a little tricky because your A term is 2x and your B term is 5. So when I have 2x to the 3rd, I've got to think about that being 8x cubed. 5 to the 0 is 1, and then the 1 for our leading coefficient. So we have 1 times 8x cubed. In our second term, we have 3 times 4x squared times 5. So what is that going to give us? 5 times 4 is 20, and 20 times 3 is going to be 60x squared. So we've got 60x squared here. And then for our third term, we got 3 times 2x to the first times 5, so that's 25. So 25 times 2, that's 50, and 50 times 3 is 150x. And then lastly, 2x to the 0 is just a 1, so we have a 1 times 125, or 125 to finish that off. Did you master that? Then in the last two examples, here's another way to think about Pascal's triangle. If you ever take statistics, you might see this definition for binomial theorem. Anytime we're expanding a plus b to the nth power, we can think of that as the combination of n items taken 0 at a time with our a to the n power. Plus the next term is going to be the combination of n items taken 1 at a time of a to the n minus 1 power. And then we're going to progress that way all the way down to the very last terms. So just reducing the a powers until we get all the way to the end, where we're taking n to the n minus 1, a, b to the n minus 1, and then finally the combination of n things taken n at a time for b to the n. So this is another way to think about that expansion. So if you're comfortable with that, or you want to take it from Pascal's triangle, 1, 4, 6, 4, 1, and we're simply looking, they're asking us to look for the third term, just the third term. Well, here's my third term coefficient. And what happens with our third term in the expansion for the a term? Well, a is going to go down by a power. So we're going to start here with x to the 4, x to the 3, x to the 2. And what's going to happen to the negative 3? Well, the negative 3 is going to go to the 0 power, and then to the first power, and then to the second power. So when you think about that expansion, and you also think about the signs alternating, so we have a plus and then a minus, and this is going to be a plus, and then a minus, and then a plus. We're looking at this column. So that third term would be a 6 times an x squared times a 3 to the second. But if you thought about it using this definition here for the binomial theorem, that would look like a combination of 4 things taken 2 at a time, and then a to the second, and then b to the second. So the combination of 4 things taken 2 at a time is 4 factorial divided by 2 factorial, and 4 minus 2 factorial is 2 factorial. So this is gone, and 2 factorial is another 2, so we could divide out this 2. 3 times 2, that's 6, which is what we had. And then our a term was x, so x squared, and our b term was 3, so 3 squared, 9 times 6, 54 x squared, and this would also be 54 x squared. So whether you use the combination approach or whether you use Pascal's triangle, either way we're going to get 54 x squared. Then finally we got one more to go just like that. Find the fourth term And the fourth term, if we did the combination, would be, let's see, the fifth row is 1, 5, 10, 10, 5, 1. So if you prefer that way with subtraction, alternating signs, plus, minus, plus, minus, plus, minus, then our fourth term, 1, 2, 3, 4, is going to be this column, and we've got to go 3x for our A and 2 for our B. So we got to think about this would be power 5, power 4, power 3, power 2, and then the powers have to add up to 5, so this would be 3. That means our terms would be negative 10, and then 3x quantity squared, and 2 cubed. So negative 10 times 9x squared times 8, so 72 times 10 is negative 720 x squared. So we're using Pascal's triangle, either finding the rows, or when they want to pick a specific term, we could find that term by using the combination of 5 choose 3 and 5 factorial divided by 3 factorial, and then 5 minus 3, so 2 factorial. So we're getting rid of that. 2 goes into 2. 5 times 2 is 10 to find this term. So whichever way you prefer. We are now finished with Lesson 7. See you next time.